A number of years ago, I had a medical issue that required that I had a nuclear blood scan. And the idea is they inject you with a radioactive material. They phoned me up 3 times that morning to make sure that I would be there because they're manufacturing this stuff at a nuclear reactor on the U of A campus. And we'll talk about how they manufacture it. This stuff has a half-life of hours, which means if I make this appointment and they manufacture it and they put it in a cabinet and I don't show up for 2 weeks, there's nothing left. So literally that morning, they're in the lab manufacturing this stuff. And they're confirming that I'm going to be there because it's an expensive procedure. What it involves is they inject this radioactive isotope. It's called Technetium 99. Technetium 99. I don't know what the M stands for. They inject it into my blood through an IV, and then they allow my body the time to move it around my body through my bloodstream, right? And the issue was to do with my pancreas and a couple of other organs, that there were some images on some imaging that didn't look right. So what they wanted to do was make sure that the pancreas was operating properly, and if it wasn't, then they wouldn't detect the radiation out of my pancreas. Okay, so they allow me to become totally radioactive, and then they scan me, tip to tail, head to toe, and they find out what's radioactive, and if there's dead spots, they know there's a problem. I was fine. It was a different issue. So me being the guy that I am, I know I'm going to be radioactive. I took the Geiger counter with me. And I had to wait around there for a couple hours for the scan. I was injected at 11:30, so I started doing measurements at 2 p.m. So I'm in my car, downtown Edmonton. People are looking at me, and I'm holding a Geiger counter. I'm breathing into it. I'm holding it against my chest. I'm holding it against my hand. I think I settled on the best reading. It was dead center of my chest. And your lungs have a lot of vascular action going on. There's a lot of blood moving around in your lungs. And it was 20,000 becquerel, 20,000 decays per second. So it was, tick, tick, and I do this, and it was just going crazy. And I took readings throughout the day. So at 3:17, which I converted to decimal hours, it was 17.5. These all seem like nice kind of round numbers because of how the scale on the Geiger counter is incremented. And it was going down. And it's going down because of radioactive decay. Every half-life, half of it is no longer there. Now, admittedly, you would extract some of this in urine and in sweat and in your breath, but most of it is trapped in your blood. And it kept going down. I think that was the last reading. This was at 5:50 the next day. So I started taking fewer and fewer readings. And I thought this would be a really interesting thing because I know what the half-life is supposed to be. So I made a graph of this data. I put this in L1 of my calculator. I put the activity in L2. In other words, I'm constructing that graph we just drew. And this is the graph. I think that's pretty cool. But I went a little further. It's possible for me to tell the calculator to find the equation of that using regression. It is not a linear regression or a quadratic or a sine or anything like that. It's an exponential one. Don't worry about what the equation looks like. This is what the equation looks like. It's more of a math thing than a physics thing. And when I plotted that equation, and don't worry about the r and the r squared, I guess I'll tell you, the r and the r squared, if these numbers are closer to 1 or -1, then that means the data is fitting the graph really well. In fact, that's what the data looks like. So I got a couple of sloppy measurements, I think, here, right? But it's pretty bang on. So what I did is I took the y-intercept of that graph and I divided it by 2, because if the y-intercept is the initial activity, this would be half of it, and that means that this time is the half-life. So 6.04 hours, experimentally. And I admit it, I'm a bit of a nerd that way. I thought this would be an interesting experiment. And when you look on Wikipedia, and I know people say, oh, don't trust Wikipedia. They're not going to lie to you about stuff like this. The half-life of technetium 99M is 6.0067 hours. I don't know what kind of percent error we're talking about there, but it's got to be tiny. It's less than 1% error. It's about 0.5% error. And I hope that by going through this with you, you gain an appreciation for how you could analyze data, because you could see this on an exam.